This lesson deals with supplemental problem 313. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 18. The circuit shown here has a PNP transistor, an NPN transistor, and 4 resistors and a power supply. This is part of a larger circuit that was published in a magazine article entitled Bootstrapped Complementary Feedback Pair. And the magazine was Nuts and Volts magazine, and it was in volume 24, number 8. And the article is called Bipolar Transistor Cookbook, Part 2. This is a collection of very practical bipolar circuits, and this idea of bootstrapping has to do with AC circuits, and we'll talk about some of those ideas in Chapter 5 and beyond. Could you find the current I and the voltage V if these were the specs of the NPN and the PNP transistor? The base emitter turn-on voltage is 0.54, the collector emitter saturation voltage is 0.2, and beta F is 66. And for the PNP, the emitter base turn-on voltage is 0.72, saturation is 0.2, and beta F is 228. Could you guess at the states of Q1 and Q2, and then check your guesses, and if necessary, guess again. The circuit's got a lot of stuff in it. Let's try to simplify it by taking this part of the circuit and Thevenizing and putting it back. That'll get rid of a loop in our analysis. We draw this down here, where I've got a 12-volt power supply to ground, a 100K resistor, a 120K to ground, and a 150K feeding the base of Q1. Let's find the open circuit voltage, or Thevenin voltage. Because there's no current flowing in here, this voltage is the same as this voltage, which is going to be 12 volts, voltage divided with 120K and 100K. 120K over 120K plus 100K times 12 is 6.55 volts. Then setting this equal to 0 and looking back in here, I see 100K in parallel with 120K in series with 150K. This is 55K, and so the total is 205K. I'm going to take and put that back into my circuit over here. I have to guess the states of Q1 and Q2. Now with this bigger resistor here, I'm going to have a very small base current. I guess probably this is going to go active. And then over here, I've got a small resistor, and I've got 12 volts. This drop plus this drop has to add up to 12. If this is a small resistor, then we won't have probably a big drop across here, and we'll have most of the 12 volts across here. And I guess that that's also active. Let's put in the active region models. I labeled the collector base emitter of transistor 1, and then the collector base emitter of transistor 2. Between the base and the emitter of the NPN transistor, we had 0.54 volts, the turn-on voltage. We have a current source of beta FIB, but this is transistor 1, so let's put the subscript on so we don't confuse the two controlled sources. And then for transistor 2, between the emitter and the base, the PNP, we had 0.72 for the turn-on voltage, and the beta F was 228, times the current coming out of the base. We have a 12-volt battery back to ground, 3.3K back to ground, and then our Thevenin equivalent circuit hooked up to the base. To check that we're active, we need to show that IB1 and IB2 are greater than or equal to 0, and that the voltage across the collector and the emitter collector are greater than or equal to the saturation voltages. Because of the current sources here, I want to find a loop that I have just voltages and currents that I perhaps know, or an expression for a current that I know. We'll go around the loop this way. The rise in voltage is 6.55. The drop is going to be IB1 times 205K. Plus 0.54, and then the current going into here is going to be IB1 plus 66 IB1, so that's 67 IB1, plus 228 times IB2, and all that times 3.3K would give me the voltage across it. I have one equation and two unknowns. I have IB1 and IB2. I have a relationship between IB1 and IB2 right here. The current that enters this node equals the current that leaves the node. So IB2 is equal to 66 IB1. Let's substitute that back in over here. Here's the same expressions, and I'm going to plug in over here 66 times 228, and then solve for IB1. It's going to be 6.55 minus 0.54 divided by 205K, 3.3K times the quantity, 67, plus 228 times 66, and I'm pulling out the IB1 from this expression. This turns out to be 6.01, and all of this turns out to be 49.88 million. What's happened with this circuit is that we've made this resistor here look like it's about 15,000 times bigger than it actually is. And controlled sources can do that. The base current turns out to be 120 nanoamps, pretty small, but that is greater than or equal to 0. And the base 2 is 66 times the base 1, so multiply this times 66 and you get 7.92 microamps, and that's greater than or equal to 0. Then I can solve for the voltage V. Over here, the current coming in here is going to be IB1 plus 66 IB1, so 67 IB1. And then I have coming in here, I have 228 times 66 IB1, we found before, and all that gives me about 6 volts, 5.986. I can solve for the emitter collector and the collector emitter voltages. This one's kind of easy. It's just going to be 12 volts minus V, which we've already found. 12 volts minus V would be 12 minus 5.986, and that's 6.014, and that is greater than or equal to 0.2 volts, so that checks. And then the collector emitter of 1 is going to be this node voltage minus this node voltage. This node voltage is minus 0.72 plus 12, and then this node voltage is V, which we just found to be 5.986, and all of that is equal to 5.294, which is greater than or equal to 0.2 volts, and so our assumption checks. And lastly, what's the value of I? That's the same as IB1, and that was 120 nanoamps. This is supplemental problem 313.